In section 4 of chapter 11. Y'all thought we were done with inverses? Wrong. They're coming back. We're now talking about the inverse of those 6 trigonometric functions. So now we're technically going to be dealing with 12 functions.
Oh wait, no, I didn't mean to.
Let's do this. First, I want to remind y'all how to find the inverse of a function. If I give you a function like f of x equals 2 times the quantity of x plus 1 divided by 7, quantity cubed minus 1, and I told you I need you to find the inverse of that function, the first thing that you would do is take the x values and the y values and swap them. Realize f of x is just a fancy way of writing y. So this is going to transform into x equals 2 times the quantity of y plus 1 all over 7 quantity cubed minus 1. The rest of this problem is us just trying to get that y value by itself. I want to get rid of everything on the right side of the equal sign besides the y value. So let's start by adding 1 to both sides. That leaves us with x plus 1 equals 2 times the quantity of y plus 1 quantity all over 7 quantity cubed. Then I'm going to get rid of the 2 that's being multiplied, so I'm going to divide both sides by 2. I'm going to go fairly quickly because this should all be review at this point. In order to get rid of the third power, I'm going to take the third root of both sides. I don't need a plus or minus because plus or minus only shows up if you're dealing with an index that is even. Don't really have enough space, so I guess I'll go back up here. This will be the third root of x plus 1 all over 2, and that's going to be equal to y plus 1 all over 7. I'm going to get rid of the division of 7 by multiplying both sides by 7. That'll get rid of the 7 in the denominator, leaving me with 7 times the cube root of x plus 1 all over 2 equals y plus 1. Subtract 1 from both sides. I'm going to move the y to the other side. I'm also going to start bumping back into inverse notation. So f inverse of x is going to equal 7 times the cube root of x plus 1 all over 2 quantity all minus 1. There is my inverse function. You are all able to do this at this point because all of these steps were algebraic. Heck, even if I threw in an exponential in here, you started using logarithms. That's still algebraic techniques. Trigonometry, on the other hand, when you start dealing with sine, cosine, tangent, secant, cosecant, and cotangent, the algebraic techniques are not enough. You have to expand your trigonometric understanding. So if I have the equation y equals sine of x, and I told you to find the inverse, the first thing you would do is you take the x and y values and swap them. That's how we solve for all inverses. So this would turn into x equals the sine of y. The issue you would all run into at this point is you do not know how to get the y out of the sine function, because out of all the stuff that you've learned in mathematics, for the most of you, you haven't learned how to do that. The y is stuck inside of the sine function. You need a new operation, a new trigonometric operation, to undo the sine function. And that function is called the sine inverse function. It is sine inverse, because sine inverse and sine will undo each other, kinda. It's a little more complicated than that. Whatever I do to the right, I also have to do to the left. Do realize that is not a negative 1 power. Trig functions are not allowed to have negative 1 powers. The reason they're not allowed to have negative 1 powers is because negative 1 powers would get the reciprocal. You already got those. The reciprocal of sine is cosecant. Therefore, this is going to turn into y equals sine inverse of x. Now, the algebraic side is relatively approachable, but once we start getting into the graphical interpretation or plugging values into the inverse, it becomes a lot more technical. Problem number 2, I have y equals cosine of x. I'm going to do the same math, swap x and y, and you're still going to get x equals cosine of y, and we're going to do the same thing, which is the cosine inverse to both sides. Because cosine inverse and cosine technically kind of a little bit cancel. That means y is equal cosine inverse of x. And this would be our answer. However, once we start analyzing the domain and range of these inverse functions, that's when it gets really challenging because there are major limitations to inverse trig functions. I've duplicated the unit circle up here. I am going to start tackling these inverse trig functions and specifically stating what their domain, or the values you can plug into the function, are, and the range, the numbers you can expect to get out of the inverse trig function. So the inverse trig functions are cosine inverse, and then we have sine inverse, and then we have tangent inverse, and then we have secant inverse, and then after that we have cosecant inverse, and then we have cotangent inverse. And you might notice I only picked two colors, and that's for a reason. It's going to be really, really important once we're done with this. Now I'm going to list off the domain restrictions because there are domain restrictions to some of these functions, and it is really important that we recognize that. But focus primarily in this class is going to be on the range restriction, what we can expect to get out as an answer. Now before I do that, I want to remind you what inverses do. For the original cosine function, the way it worked is you take cosine of an angle and it'll produce the x value of a coordinate. Cosine inverse is the inverse of that process. Cosine inverse operates by saying cosine inverse of the x value of a coordinate will give you the angle that created it. So notice how that's different. Cosine, you plug in an angle, it'll output a coordinate. Cosine inverse, you plug in a coordinate, it'll output an angle. But there's an issue with that. There's a big, big issue with that. Because for cosine inverse, you first have to ask yourself, well, if cosine inverse is talking about the outputs, the numbers we can get out of cosine is kind of trapped. Cosine is the x value. The smallest x value you can get from cosine is -1. Because if this is on an xy axis, the furthest you can go left is here on your unit circle at -1. -1 is the smallest answer you can get for cosine. Therefore, for inverse cosine, -1 is the smallest number you can plug into cosine inverse. If on a calculator you take the cosine inverse of 2, it'll say undefined. If you take the cosine inverse of -13, it's undefined. The cosine inverse of -1.1 is undefined. For cosine inverse, you can only plug in numbers from -1 to the biggest value you can get on cosine, which is all the way to the right, which is 1. That's the domain restriction for cosine inverse. So if you're trying to solve these, first realize that if you're writing a cosine inverse function, the only thing you can have in the parentheses are numbers between -1 and 1. If you try and do anything else, the problem will break apart. For sine inverse, the same thing, but we're talking about the y values. The smallest y value that sine can take on is all the way down here at -1. The biggest it can get is all the way to the top at +1. So it has the same domain restriction. But now's where we get to something a little bit more wonky. Tangent is defined as the sine value over the cosine value. Because those are both fractions, technically, tangent can be anything from -infinity to infinity. That won't make a whole lot of sense because we haven't discussed the graphical or the domain too much of the interpretations for tangent. But if you mess around with it enough, you'll realize tangent can output any answer we want. Secant is where it gets even more weird. Secant is the reciprocal of cosine. That means that its domain is going to be from negative infinity all the way to negative 1, union 1 to infinity. If you took the domain of cosine inverse and its reciprocal secant inverse, it would be the entire number line. So for secant inverse, you can plug in any number you want as long as it's not between negative 1 and 1. So you could plug in the 5 or the 7 or the 13 or pi. You can't plug in 1/2. You can't plug in 3 over 4. You can't plug in negative 8.6. Sorry, negative 0.86. And then cosecant inverse, it is dealing with the same domain. It is negative infinity to negative 1, union, that's a bracket, 1 to infinity. And then lastly, cotangent has the same domain as tangent, which is it exists for all real numbers, negative infinity to infinity. But our primary focus in this class is going to be the next column, the outputs, because I will be giving you problems that say, what is the cosine inverse of root 3 over 2? That's me saying, what cosine value has a coordinate of root 3 over 2? So I'm going to give you the coordinate, you got to tell me the angle. There's a problem with that. Let's use my example. If I say cosine inverse of root 3 over 2, I'm saying, where on the unit circle is the x value root 3 over 2? There are two locations where that occurs. That occurs at 30 degrees, and it occurs at 330 degrees. That's a problem. We only want one answer. Technically, if you start thinking about coterminal angles, angles that also exist at the same location on the unit circle, I could go to 30 degrees, but if I go another full rotation around the circle, which takes me to 390 degrees, they both have the same answer. So technically, if I don't restrict the range at all, cosine inverse has an infinite number of solutions. Mathematicians don't like that. So we say, all right, there are way too many answers. We are going to restrict for the inverse trig function. We're going to state we only want answers over a specific region. Otherwise, there's way too many answers. So for cosine inverse, we say, all right, what region on the unit circle encompasses all of the possible x values that you can get? Well, it's all the coordinates from here. Here are all the positive ones, and then here are all the negative ones. So for our range, for our answers that we can get out of an inverse trig function, they can only exist from 0 to pi. Because 0 to pi includes all of the possible inverse cosine values. Anything after pi, we would repeat numbers that are already present between 0 and pi. Sine inverse has a different problem. I need to come up with a range restriction, a list of an area on the unit circle that encompasses all of the y value answers. I need all the positive and negative y values. Here's our issue. All of the positive y values can be represented in the first quadrant, but then the second quadrant is also still the same positive y values. So going from 0 to pi doesn't cut it, because these are repeated y values. So it would be from 0 to pi over 2, and then pi over 2 to 3 pi over 2. However, mathematicians are lazy, and we don't like writing this as an interval from this range and from this range. We want just a single range. So what we did instead is we said, like, well, okay, let's instead say it's going to go from, oops, wrong color, from here, because this represents all the negative y values all the way to here. This is going to be the range for sine inverse, because that includes all the negative y values for the coordinates and all the positive y values for the coordinates. So their restriction is it has to be from negative pi over 2 to positive pi over 2. And now's the point when you might also be wondering, Mr. Silva, why were you only using red and blue this entire time? Because our focus is on the range. All of the red functions that I have written have the same range. All of the blue functions have the same range. How do we remember that, Mr. Silva? Because all of the red functions have something to deal with cosine, which is the x value, which is why the range is left to right. It's in the x direction. All of my blue functions, like sine, tangent, and cosecant, deal with the y value. Y is up and down. That's why the range on my unit circle is the right side of the unit circle. It's the side that is up and down from one another. So tangent and inverse, that range is negative pi over 2 to pi over 2. Secant inverse is 0 to pi. Cosecant inverse, negative pi over 2, positive pi over 2. And then cotangent inverse is 0 to pi. The way this is going to affect you, at least in this class, and in pre-calculus it'll affect you even more drastically, but in this class, if I ask you, for example, what is the cosine inverse of 1/2? I'm saying, when is cosine equal to 1/2? Cosine is equal to 1/2 here, but it's also equal to 1/2 here. But because I said that cosine inverse only exists between 0 and pi, we ignore this angle down here for cosines. We only focus on the top half of the unit circle, because we don't want duplicate answers. I don't want you to tell me, oh, Mr. Silva, it exists at 60 degrees and at 300. I just want one answer. That's why we have a restriction on the range. It restricts you from giving me multiple answers. There's only ever going to be one. Problem number 1, it is asking, what is the cosine inverse of negative 1/2? That question is asking, when is cosine, the x value on the coordinates, going to be negative 1/2? Well, cosine is negative 1/2 at two locations. It is equal to negative 1/2 right here, and it is equal to negative 1/2 right here. However, cosine inverse is only defined from 0 degrees all the way through to 180 degrees, or 0 radians to pi radians. So we ignore all answers that are not in that region. So the only one solution we have is this dot, which produces an angle of 4 pi over 6. That's our answer. Problem number 2 says sine inverse of root 2 over 2. That is asking, when will the y value, the sine value, be root 2 over 2? Again, there are two locations. It'll be root 2 over 2 here, but also here. However, sine inverse is only defined from negative pi over 2 all the way to positive pi over 2, or negative 90 to positive 90 degrees. Therefore, I'm ignoring all answers outside of that region. There should only ever be one answer. So the sine inverse of root 2 over 2 is going to occur at that coordinate, which is pi over 4 radians. Problem 3, tangent inverse. It is saying, when is the tangent function going to output an answer of negative root 3? Tangent will output an answer of negative root 3 when it becomes negative root 3 over 2 divided by 1/2. So it's when the sine value is negative root 3 over 2. The sine value will be negative root 3 over 2 here and here. Here, and then the other one also needs to be positive, so the other one would be, oh no, it would just be that location. So that is going to produce that as a coordinate. That coordinate is not going to be 10 pi over 6. That coordinate is going to be negative 1, 2 pi over 6. Negative 2 pi over 6. Problem 4, I'm dealing with the secant inverse of 2 root 3 over 3. Now that might look super complicated because it's saying when is the secant value going to be 2 root 3 over 3, which is saying when is the reciprocal cosine going to have a coordinate of 3 over 2 root 3. Notice that there's a root 3 in it. Root 3 will only show up if the coordinate had a root 3. That would only occur for cosine when cosine is root 3 over 2. So for problem number 4, I'm looking for when the cosine has a root 3 in it and it's positive. That'll occur here. And that would also occur here. But secant is only interested in values in the top region. So I ignore this. The answer will occur at this dot, which is at pi over 6 radians. And then lastly, but certainly not leastly, we have cosecant inverse of negative 2. That is saying when is the cosecant going to have a value of negative 2 for its coordinate. Cosecant is the reciprocal of sine. Get the reciprocal of negative 2 is negative 1 over 2. So it's saying when is the sine value going to be negative 1/2? The sine value is negative 1/2 here and here, but cosecant is only defined on that region on the right side, so I ignore that value. This is the only coordinate that satisfies it. The answer is not going to be 11 pi over 6. We use the negative coterminal, so we're going down one slice. That means negative pi over 6 is our answer. Of course, you could also give your answers in degrees, but once again, my recommendation is that you learn to slowly avoid using degrees and start integrating more and more radian measures into your mathematics. I will tell you in the long term, it'll save you a ton of time and energy and headache.